Teşekkür ederim.
Evet.
Okay, so we start with the definition. A mapping F Rn to Rm is called regular if the tangent map F star P is one-to-one at all tangent spaces. At all points or tangent spaces. Okay. Okay. Let me also remind you the inverse function theorem. So here, let f is a function from Rn to Rn, okay? Be a mapping, so it's a differentiable function. Mapping. If the derivative map is one-to-one, well, of course, if it is one-to-one, derivative map is a linear map from an n-dimensional space to an n-dimensional space. And if it is one-to-one, since the dimensions are the same, it is also onto. Therefore, F star is indeed an isomorphism, okay? One-to-one, indeed an isomorphism. Because both spaces are Rn, okay? It's a linear map from an n-dimensional space, linear map to an another n-dimensional space. Both has the same dimension. It is linear. Sorry, it is one-to-one. Therefore, it has rank n. And since the dimensions are the same, rank n map is also onto. Therefore, this map, linear map, F star, is both one-to-one and onto. Therefore, it's an isomorphism. And the inverse function theorem tells us the following. If the derivative map is an isomorphism, then F is also isomorphism, but that is only true locally. So what we mean is this. At a point P, then there is an open subset. Open subset U containing P so that F is a diffeomorphism. Diffeomorphism from U onto an open subset V in Rn also. Okay, so let me draw a picture of what's going on. Ya da ilk önce şöyle kalsın. Şurayı silerken yapayım onu. I'll tell you. So this is what happens. So here I have Rn, and then I have the map F into Rn again. So they have the same dimension. And here I have a point P, and this point is mapped to some other point F of P. And I look at the derivative map at this point. The derivative map is a linear isomorphism. It is one-to-one, and therefore it is onto, and it's a linear isomorphism. Then the statement of the inverse function theorem is the following. If F is an isomorphism, if the derivative of F is an isomorphism at a point, then actually it's an isomorphism. F is an isomorphism, whatever it is, around this point. So how do we say that? There is an open set containing this point, U, and there is an open set containing this point, V. And if you restrict your function F to this open set, let's say this, it has an inverse. This F may not have an inverse, but its restriction to this open set has an inverse. I should write it this way. Inverse of this restriction exists, and both of them are differentiable maps. Okay, both maps F and its inverse are both differentiable. So that's a differentiable actually infinitely many times. So when I say a mapping, I mean it's differentiable as many times as you want. So it is infinitely many times differentiable. And if F is infinitely many times differentiable, then so is its inverse. That's a part of the theorem. And if you have this situation, then we say that F is a diffeomorphism, okay? So what's the diffeomorphism? It's a map from an open set to another open set. It is one-to-one and onto, and both the function and its inverse are infinitely many times differentiable, okay? So diffeomorphism, here, a diffeomorphism means that okay, it's a function. It is a one-to-one and onto function from an open subset to another open subset, so that both the function and its inverse, since it is one-to-one and onto, it is an inverse, and we assume that we require that both the function and its inverse are differentiable, are infinitely many times differentiable. So a diffeomorphism is this, okay? A diffeomorphism is a map from an open set to another open set. It has to be one-to-one and onto, and both the map and its inverse are differentiable infinitely many times. So you may take derivative as many times as you want. Okay? And that's the statement of the inverse function theorem. And actually, inverse function theorem gives, shows the power of the derivative map. It says the following: if the derivative map is an isomorphism at a point, then the function is actually a diffeomorphism around that point. Not just at this point, but around this point. Yani bir noktadaki lineer izomorfizm diyor ki o noktanın civarında sizin fonksiyonunuz diffeomorfizmdir. Diffeomorfizm deyince tabii yani diğer bütün noktalarda da, şuralarda da bu türev map hep isomorfizm. Çünkü türev map'in isomorfizm olması bir determinant koşulu değil mi? Determinantı non-zero olacak. O open bir condition. Bir noktada sıfırdan farklıysa civarında da farklı olacak. Continuity'den dolayı. Yani her noktada türev map'i isomorfizm ama hani fazlası var. Bu map ve tersi ikisi de sonsuz kere türevlenebilir. Dolayısıyla türev map'i yani derivatif map noktadaki bir özelliği bütün open set'e taşıyor. O yüzden hani türev map'i çok kuvvetli bir şey. Evet. Well, if it is a diffeomorphism, then it's by definition a homeomorphism. Yeah, I mean, if the dimensions are the same, if it is a homeomorphism, then the dimensions are the same. Yes, you're right. So your friend is asking this. Suppose we have a function. Suppose we have a function and a homeomorphism between these two open sets. These are open sets. This is inside in some Rn, and this is inside in some Rm, let's say. If F is a homeomorphism and if it's a smooth map, actually, if it's a homeomorphism, then n equals m. This is difficult to prove without further assumptions. Just if you use homeomorphism, to prove this, it is not easy. Okay, it's a well, it takes a couple months actually to prove it fully. But if you know that F star is an isomorphism, then this is very easy because I have a tangent vector at this point, tangent space at this point. This is smooth, means the map is well defined, that we have derivative map, right? And if it is an isomorphism, then the dimensions of these tangent spaces must be the same. And the dimension of the tangent space here and here m, therefore n should be equal to m. Your friend asks the following: if this is a homeomorphism and if this is a smooth map, then it means, well, of course, I assume that F star must be invertible at the point P. Then by the inverse function theorem, F is a locally homeomorphism. Well, actually, you are asking something more than that, I guess, right? Yeah, but yeah, at each point it is differentiable. Then yes, you are right. Okay. Yani bu bir homeomorfizmse, türevi de varsa ve sıfır değilse türevi, o zaman diffeomorfizm de olur. Çünkü inverse function theorem onu söylüyor. Türev mapi isomorfizmse o zaman bir open sette bu diffeomorfizm. Sizinki her noktada şeyse, bu türev sıfır değilse, o zaman yani türev mapi isomorfizmse o zaman şey olacak. Diffeomorphism olur. Okay. Well, we have seen how a map and its derivative carries tangent vectors. If a map carries tangent vectors, then it also pulls back the objects which its tangent vectors. In other words, differential forms. And let's see how it works. So pullback of differential forms. You see, I have a function from, let's say, Rn into Rm, not necessarily the same dimension. And here I have a point. Its image is over here. And if I have a tangent vector here, then it is sent to a tangent vector here, right? This is f star p evaluated on the vector v. And now suppose I have a one form here. One form. What does a one form does? It eats vectors and gives us real numbers. Well, I can do the following. I may start with this. First, send it over here via the derivative map of f, and then feed it into this one form and obtain a real number. So I start with the tangent vector and end up with a real number. And this map is linear at each point because f is linear. Its derivative map is linear. And this is a one form. It is also linear. Therefore, this composition from this tangent space. So I have the tangent space. And then here we end up in the tangent space. And then I take the one form and end up in R. This map is linear. This is the F star map at P is linear. Therefore, this composition is linear. It takes this vector into F star V and then phi of F star P V. Okay. This composition has a name. It's a one form on this tangent space because you take a vector here and obtain a real number. It's a one form on this tangent space. And of course, it uses this gadget. Therefore, it is called the pullback of this one form. Why pullback? Because I go in the reverse direction, right? I go from Rn to Rm. So you are just pulling back the one form. So, and the notation is this. We denote it this way. We say that this is F star. This is the notation, okay? Phi. This is the pullback of phi via F. And then you compute this at the vector V. Pullback of the one form. Phi via F. Daha doğrusu şu pullback. Bu da pullback one formun değeri, right? This is the value of the pullback one form at this point. So pulling back the one form is nothing but actually pushing the vector, from this space to this space. Sorry? Yeah, I may. Okay, this is actually something you already know from calculus. And if you think about it a little bit, so what you do, you are just actually going with the derivative of f, and then you just feed that vector into the one form. So let me do one example. Let's say f is a function from first R to R, both one-dimensional, and suppose it is given by, okay, yeah, önemi yok. So at any point P, any mapping, and phi is a one form. One form means what? One form is just this. Some function ax dx, right? One form is this. I have only dx, and here I have ax. Bunu da şöyle çizebilirim. This is one dimensional, so we may just draw it like this. And here I take a vector and send it to f star v. What is f star v? Well, f star v is just the derivative of f. It's a one by Jacobian matrix is just one by one, and it is a single entry. It is just the derivative of f, right? You may think this is nothing but the derivative of f evaluated at the point P. It's a real number times this vector, whatever that is, okay? So that vector. Bu ne demek? Derivative of f prime. Değil mi? Jacobian matrisi bunun nedir? Birebir bir matris. Sadece f'in türevi var. Bir değişken var. Dolayısıyla Jacobian matris birebir. Onu bir vektörle çarpıyorum. Teğet vektörü de birebir. Bu aslında iki tane reel sayıyı çarpıyorsunuz demek. Türeviyle bu vektörü çarpıyorum. Peki one formumuz nedir? One formumuz şu. Phi. Bu vektörü alıyor. Şununla buna yediriyor. So phi of f prime v. So what is this? This is just a at the point. So at which point we have at this point x is equal to q. So aq, and then I have dx evaluated on this. Also this is a real number. It goes out. So f prime at p, and then I have just dx evaluated on this vector. Yes. Yani ne demek bu? Okay. Şöyle mesela bir örnek yapayım. F diyelim ki, suppose f is this, x squared plus 1, x squared plus 1, and phi is the one form. Let's say just the x. So şeyi belki karıştırmamak için şöyle yapayım. Şuna u diyeyim. U squared plus 1. And this is my x. So I have here the point u, and this is mapped to x, which is u squared plus 1. U squared plus 1. And here I have the one form, just dx. So ax is 1. So what is f star of phi? So f star of dx, that is nothing but okay. Bir dakika. Okay, so this should be just df. Yeah. So, or we actually in calculus we write du. So what is du? No, not du. Bir dakika, bunu nasıl yazacağım? Yok, hatta şöyle yapmam lazım. Tamam, bu okay, so this is df. df is just the u squared plus 1, and this is just 2u du. Okay, so what it does, yes, so if you have a vector here, the derivative of this gadget, so f star is given by the derivative of this, which is just multiplying by 2u, right? Here I have this f star map. F star map is a 1-by-1 matrix given by 2u. So when you have a vector here, you multiply its that vector by 2u, and then you will feed that vector to the one form dx. Okay. Yani bu f şunu yapıyor. F'in türevi vektörün boyunu, değil mi? Hangi noktadaysanız o noktanın koordinatının işte 2 katını alıp onunla çarpıyorsunuz. Yani vektörlerin boyunu değiştiriyor. Ondan sonra da onun dx'ine bakıyorsunuz. Yani şeyde one formda hesaplıyorsunuz. Dolayısıyla so in the computation of pullbacks, this is what you do. If you are given your function like this in coordinates, then dx is just so x is equal to, let's say, u squared plus 1. this is the expression, right? F of u. Then dx is just df, which is just 2u du. Okay, so computational wise, it is nothing but what you have seen in calculus. And in two variables, it becomes better. Why is that? Let's see. Another example. Suppose you have a function from R2 to R2. And let's say it's given like this. F of uv, f of uv is just 2uv and then u squared plus v squared. Here I regard them as x, y. So here coordinates are u and v, and here coordinates are x and y. Okay. All right. So x is just 2uv, y is just u squared plus v squared, right? And then if you want to compute the pullbacks, what you do, you just, do as if you are changing coordinates. So what is dx? Dx is this. You take derivatives of this gadget with respect to u and v. So first take derivative with respect to u. Şey gibi, yani Jacobian hesap eder gibi. X is a function of uv. You compute its differential. So what is that? This is del x del u du, del x del v dv. So what is that? It is just derivative with respect to u is just 2v du plus 2u dv. What about dy? So this is del y del u du plus del y del v dv. So it is this time 2u du plus 2v dv. Okay. So these are the pullbacks of the one forms. Here I had the one form dx, its pullback. So its pullback is just this. So this is just f star of dx, and this is f star of dy. There are one forms now on this R2 where the coordinates are u and v. And the nice thing is this. If you want to compute dx wedge dy, let's see what you get. What about, so the two form, so f star of dx dy. Let's compute it over here. So so it will be just I am not explaining, fully the theory, but I'm just explaining you the manipulation. And this is something you already know. So this, pushing vectors forward or pulling one forms back, they are not actually something, new. They are, the stuff you already know from advanced calculus. So what you do, you just take this 2 and form the wedge product. So this is 2v du plus
Pardon hocam.
2u. Yes.
Kamera arkada kaldı.
Özür dilerim. Okay, so f star dx wedge dy, it's, separates like this. And then I write just this 2 expression. F star dx is just 2v du t 2u du wedge 2u du plus 2v dv. Right. And then you form the wedge product. Well, I have 4 uv du wedge du plus 4 v squared du wedge dv plus 4 u squared. Evet. Şurası değil mi? Tamam. Okay. 4 u squared dv du plus 4 uv dv wedge dv. Well, we know that, this is 0 and this is 0. And du dv and dv du are inverses of each other. So this is just minus du dv. So the whole thing is then equal to what? So that's equal to just, so f star dx wedge dy is just yes, so it is 4u squared plus 4v squared, no, minus 4v squared du dv. So it is, all right, 4 v squared minus u squared du wedge dv. This is the formula you use when you are taking integration. You make a variable change, and then you have to compute the Jacobian. Okay, this is the Jacobian. So if you work with forms, Jacobian comes for free, this gadget, because you already take derivatives when you are computing pullbacks, and then when you take the wedge product, that is determinant. Wedge product is basically determinant. Therefore, you get the Jacobian. This is nothing but the Jacobian, actually. So let's compute the Jacobian you remember from advanced calculus. So f is what? F was this map. Fx, no, f uv is just 2uv u squared plus v squared. So what is the Jacobian of uv? No, so I regard this as xy. So Jacobian of the new variables with respect to the old ones. Okay, so it is just this matrix, değil mi? İşte bunların derivative of x with respect to u, 2v, and then derivative of x with respect to v, 2u, derivative of y with respect to u, 2u, and the derivative of y with respect to v, 2v. And you take the determinant of this. So determinant of this, it is just 4v squared minus 4u squared. Exactly this expression, okay? So all we have done is actually, same old advanced calculus written with some fancy, words, names. That's it, actually. Although it seems, this kind of notation seems more confusing. You see, even I get confused sometimes. Although it has such a disadvantage, it is very advantageous when you use them in differential geometry. The thing is that working with tangent vectors is not actually very practical, because you cannot push forward vector fields. 2 points may be mapped to a single point, and when it happens, you don't know. So suppose you are at this point and at this point, and you have a vector here and vector here, and your function, let's say, takes these 2 points to the same point. This function doesn't have to be one-to-one. And if this is the case, then will you take the image of this one or this one? So you cannot push forward vector fields, because you don't know which one you will take. Will you take the image of this one or this one? Image of this one might be this, image of the other one might be something like this. You don't know which one to take. So you cannot push the vector fields forward, but you can pull the one forms back, or differential forms back. Therefore, they are more advantageous. That's why, we are using the language of differential forms in geometry. Not vector fields and so on, but differential forms, okay? And although, it's a little bit confusing, it has several advantages. Actually, computational wise, it is something you already know from calculus, right? And here is the proof. You already knew this gadget, variable change, and pullback is nothing but variable change, actually. But it is more general than that, because in variable change, you usually go from, let's say, R to R, or R2 to R2, R3 to R3, right? When you make variable change, the number of variables must be the same, from 2 variables to 2 variables, 3 variables to 3 variables. But differential forms, pullback is much more general. You may go from Rn to Rm, okay? It is well defined. So pullback is something much more than just variable change. Anlaşıldı mı? Biraz kafanız karışıyorsa bu iyi bir şey. Kafanızın karışması. Ben hep söylerim, yani matematik öğrenme işi bu eşya taşıyan kamyonların yaptığı işe benzer. Hani ders anlatımı. Hani işte gelir o şeyler, taşıyıcılar salonun ortasına bütün eşyayı koyar giderler. Ders anlatmak da öyledir. O yüzden de kafanızın karışması doğal. Sonraki zamanda sizden beklenen nedir? O eşyaları alıp böyle tek tek işte olması gereken yerlere yerleştirmek. Onu yapmazsanız o evde yaşanmaz. Değil mi? O yüzden kafanızın karışması iyi ama ondan sonra siz işte çalışarak diyeceksiniz ki işte bu tuzluğu buraya koyacağım, şunu buraya koyacağım, televizyonu buraya koyacağım. Onları yerlerine yerleştireceksiniz. Yapacağınız iş o. Kolay bir iş mi? Değil. Benim yaptığım dediğim gibi sadece salonun ortasına bütün eşyaları yıkmak. Geri kalan iş size kalıyor. Yapmazsanız bir hafta sonra orada artık yaşanmaz hale gelir. Her şey birbirine girer. O yüzden kafanızın karışması iyi bir şey. Kafanız karışmıyorsa o daha tehlikeli. Yani o zaman hani eşyaları da görmüyorsunuz demektir. Yani karışmasında sakınca yok. Ama uğraşarak onları sonunda düzelteceksiniz. Okay, so I'll stop at this point. Next, well, Wednesday we will start so-called frame fields, and hopefully we will start study of curves. Görüşürüz.